Photoelectric homework 1, number 7 and 8. Alright, let's start with 7. So 7 says light with a wavelength of 95 nanometers shines on a selenium surface which has a work function of 5.9 eV. The ejected electrons have some kinetic energy. Determine the maximum speed, Vmax, with which electrons are ejected. And so first they give us a few values we need to convert, which is seen right here. And once you convert them, you have the original function, which is E is equals to HF, and you can sub in C over lambda for F after converting the original function. And once you do that, you plug in the values you were given, and you're left with the energy is equals to 2.09 times 10 to the negative 18th joules. From there, we're trying to find KE. Yeah, we're trying to find KE so we can find the speed. And using E is equals to KE plus W, we convert to find KE, and this is it right here. And after that, we can plug it into the formula to find frequency. And after we find frequency, we plug it into V is equals to lambda times F. And then we're left with this value right here. Moving on to 8. Sunlight whose visible wavelengths range from 380 nanometers to 750 nanometers is incident on a sodium surface. The work function for sodium is 2.28 eV. Find the maximum kinetic energy, Kmax in joules, of the photoelectrons emitted from the surface, and the range of wavelengths that will cause photoelectrons to be emitted. So we're given two wavelengths and one value in electron volts. So we convert the two wavelengths and the value in electron volts. And then we have the function to find EV. I mean, not EV. We have the function to find KE, my bad. And we substitute E in with H times F, and we substitute F with C over lambda. And after we do that, we get this value right here, which should be KE, my bad. All right, and after we find KE, we can then use the formula E is equals to HF, and once again sub in for F, and then we're just now solving for lambda. And as you know earlier, so basically we for sure know that this value is going to be in the answer because that it's a shorter wavelength, which means it has a higher frequency, and that also means more energy. So we know this will be included in the answer. So we just want to find from here to where it will cut off. And so then after that, once we get this value, we'll know where it cuts off. So once you solve for lambda using this function that I talked about before, lambda is equals to HC over E, we then get 5.45 times 10 to the negative 7 meters, and then we convert to nanometers. So we're left with that 545 nanometers. So then we know the range is from 380 nanometers to 545 nanometers. And that's it.